Okay, so that was linear, exponential, and quadratic models. And it looked at graphs, equations, and tables for how to represent linear, exponential, and quadratic models. And so here were some of the takeaways that I noted when I watched this video a couple of times. I started writing down kind of some notes. And this is not on your guided notes, and you don't necessarily need to copy it down, but I just think that it's good to kind of review what you heard. The video does move fast. Like I said, it might be a good idea to watch it a second time on your own. So takeaways. Fun Island has a common difference, and that is a linear function. When we look at tables, I'm going to show you what it looks like. Great Island has a common ratio, also called a multiplier, which created an exponential function. And Pretty Island, which is by parabola, has a common ratio. Oh no, that one's not the parabola. Q's parabola. P is another exponential. It has just a different multiplier. And so this one gets bigger faster, which is why it's the one that gets the largest in the end. And then Q is the parabola, and we have what is called a common second difference. The video called it the difference of the difference. It could also be called the second difference. It means the exact same thing. Okay, and then these last two notes were kind of summed up in the end. It says exponential functions will always grow faster than any other type of function. All right, exponential growth is larger than quadratic growth, which is larger than linear growth. Would you please write down some version of one of the two last bullet points? You need to know this. It might be on a test. So one of these last two or both of these last two if you want, but something that tells you that exponential function growth is larger than all the rest. Make it even bigger. Sorry, it's kind of small. There we go. You squeeze it on the top or on the back or on your notebook, wherever it fits. The last two bullet points there, I want you to write a summary or write them both down or pick which one that means more to you. You need to know that exponential growth gets bigger faster than all the others. Your assignment today includes matching. And so you are going to be identifying if a graph is linear, a quadratic, or exponential. You're going to be identifying whether an equation is linear, quadratic, or exponential. You're going to be identifying whether a table is linear, quadratic, or exponential. And so hopefully these notes will serve as a good tool for that. Nope, you are just identifying. Yeah. This is a nice kind of, I don't know, I feel like it's a nice section to end on. They're right there too if you want to write those down. Okie dokie. All right, so you might get a little dizzy as I go through this, but we're gonna go kind of through this entire thing. A lot of this is already written for you, so a lot of this is just gonna be paying attention and kind of looking at what we've got here. So we've got three different kinds of functions, right? I've got linear, I've got exponential, and I've got quadratic. And we're comparing, all right? Linear means line. Exponential, right? If you think about exponential growth, well, a lot of times you think about like population or bacteria. And then quadratic. When we talk about quadratic in real world problems, usually the quadratic is actually opening down and it's like the path that some projectile takes. All right. I'm going to trace over these so that you can see. So it's this line shape. This is, oops. exponential growth that gets bigger, bigger, bigger really fast, or smaller really fast if it's upside down. And then quadratic, you have this U shape. Did you get what you needed? Okay. So how do I identify equations? There's gonna be a bunch of equations in your assignment, and you have to identify what is what. So how do we identify the 3 different kinds of equations? All right. When we study linear functions back in Math 1, you look at least 2, maybe 3, depending on your teacher, different forms of slope-intercept form. All right. So you've got these 2 equations here. We've got slope-intercept form. We've got standard form. There's also point-slope form, which is not listed here. That's okay. The identifying feature of a linear function is that I have an x with no exponent, with an exponent of 1. All right, so it seems thick. X to the power of 1. So if you look at an equation that happens to be linear, you are going to have an x and maybe a y or f of x, either one, doesn't matter, all right? But with that x, the exponent right here is going to automatically be a 1. So it's identified by not having anything in that position, but when there's nothing there, it's automatically x to the first power. All right, so identifying an exponential equation. The variable is in the exponent spot, in the exponent position. So your x is going to be a power. And if I have some equation where I have a variable in the exponent, that is automatically going to be an exponential function. Like if I have y equals 2 to the x. Or f of x equals 4 to the x, minus 5. You can have other stuff going on. As long as I have that x in the exponent position, that's going to represent an exponential equation, an exponential function. And then hopefully what you're most familiar with, because we've been talking about it for the last couple of weeks, is the quadratic. What is my defining feature of a quadratic? What am I looking for if I want to identify a quadratic? Does anybody know? I will have a vertex, but that's not easily like something that I can point out from the equation. Identified. This is when I have to have the squared, right? So I have x to the power of 2. And sometimes that means that x is squared directly, like right here, this is x squared. Or sometimes that means that this whole thing with an x is squared. But either way, this is x to the power of 2, and this is x to the power of 2. Anytime I have an largest exponent is a 2, x with the largest exponent is a 2, that is going to be a quadratic. Are there questions on identifying equations for linear, exponential, and quadratic? Not yet? Okay, if you come up with questions, let me know. I want to help. Your test on this is a week from today. Yay. Okay, so now let's look at tables. In my experience, tables are the hardest part. Okay, so it talked about in the video, and I wrote it down here above here, but that's okay. I didn't write it down. That if I have a common difference, it's a linear function. If I have a common ratio, it's an exponential function. And if I have a common second difference, it's a quadratic. And that's what that's the information that we're gonna use right down here. Right, so what does that mean, the difference? Well, first off, this only works, comparing these tables only works when the x values are consecutive. So you'll see here that I have an x value of 0, 1, 2, 3. Oh, 4 is missing. That's because it's a typo. So help me out. Cross that out. It doesn't work if it's not consecutive. Next one, 1, 2, 3, 4, 5. Okay, it works. And then -5, -4, -3, -2, -1. Yes, those are all consecutive. The common first difference, or the common first ratio, the common second difference, is only looking at the y values. And so I am analyzing on the y column, or f of x, same thing. Can I add something, or can I multiply by something to get to the next number? I always check for addition first because it's easier. All right, so here's what I'm doing in my head. I'm asking myself, how do I get from -4 to -1? Ooh, I want to add, I'm looking for a number that I can add. Now, let's be real. You've been practicing negatives for a long time, but sometimes we still get stuck with them, right? Okay, so let's start somewhere else. It's 3, right? Okay. If I start somewhere else, that's okay. How about we do this? What do I need to add to get from 2 to 5? 3. Oh, see, comes faster, right? What do I need to add to get from 5 to 8? 3. Let's see if that works above. Right now that we know what we're looking for, it might be easier to identify. From -4 to -1. Let's see, if I do -4 plus 3, does that give me -1? Yeah, it does. If I go from -1 and I add 3, does that give me to 2? Yeah. So sometimes if I start with the positive numbers, it just makes it a little bit easier. Otherwise, you could rely on a calculator, right? Oh, look, this is called a common difference. Common meaning the same number. All right, so we'll call this the common first difference. And the common first difference means that it is a linear function. So if I'm throwing tables at you and I'm like, oh, look at all these tables, which one is linear? You are going to look for something that has a common difference in the y value. As long as we have consecutive x values. That was my bad. And I found that mistake last year and forgot to correct it. Consecutive x values. Silly me. Okay. I'm going to go out of order. Don't get mad. I'm going to skip over to the third column, to the purple column. All right. I want to find the common difference or common ratio. This is my tactic. It doesn't have to be your tactic. I will always, when I see a table, I will first check for the first difference, then I'll check for the second difference. And if those don't work, then I'll check for the ratio. I just go in order from easiest to hardest. Because if it's easy, then I can just eliminate that possibility. Okay, so here, all right, I'm gonna try a difference again. So a common difference means I'm adding or subtracting a number. So from 0 to -3, I subtract 3. From -3 to -4. And if you get stuck here, feel free. Draw a number line on your paper. It's okay. Rather you rely on some of our basic skills and get it right. Okay, so I'm going from -3 to -4. If I'm going to the left, that means I have to subtract. I go from -4 to -3. Oh, that's adding 1. And then -3, I get back to 0, is adding 3. These are tough to do in your head. It is worth getting out a scratch piece of paper on your assignment and at least copying down the y column. The y column of the table, so that you can use your pencil to like, oh, am I adding a number? Oh, am I multiplying a number? Okay. Oh no, I don't have a common first difference. All right, let's try the common second difference. That just means I'm taking the difference of the differences. Whoa. So these numbers that I just found, I found a difference, boop, 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 right here. Now I'm gonna find the difference of these numbers as like layer 2. All right. So let's see, from -3 to -1, add 2. From -1 to +1, add 2. From 1 to 3, add 2. This is called a common second difference. It's not the first difference, it's the second difference. Can I keep going? Yes. The third difference, if you had a common third difference, that would be indicative of a cubic function. If I have a common fourth difference, that's indicative of a fourth degree polynomial. Nothing we're gonna talk about this year, but like this keeps going. This is just building blocks, right? So I'm gonna give you a bunch of tables. You're gonna find the common first difference. If it's the same number, yes, good, it's linear. If it's not, try the second difference. If it's the same number, great, it's quadratic. If it's not, then it's gonna be either exponential or none of the above. So how do I identify exponentials? I'm gonna write some things in green. Don't write this down. Here's what I would do. I would look at this and I go, okay, I want to try my my first difference. 2 plus 3. Oh my gosh. All of these pens are set thick because of graphing. Okay, let's try this again. From 2 to 5, okay, I add 3. From 5 to 12.5, I add 7.5. To get to 31, I'm going to add, is it 18.5? To get to 78, you're not writing this down, right? Don't write it down, right? Don't write it down. 47. Okay, so I try the first difference, it doesn't work. So then I try the second difference. What do I have to add to get from 3 to 7.5? 4.5. What do I have to add to get from 7.5 to 18.5? 11. Stop. First difference didn't work, second difference didn't work. Erase. Okay. So when the first difference didn't work and the second difference doesn't work, now I'm going to look for the common ratio. The common ratio is a multiplier. So 2 times what gives me 5? Oh, it'd be so much easier if they were nicer numbers. Okay. 2 times what gives me 5? It's going to be 2.5, but maybe that doesn't come to your head. All right. The other way to do this, here's the cheater way, right? Instead of asking what times this gives me the number, I'm just going to use division, right? Because multiplication, division are inverses of each other. And so I'm going to do 5 divided by 2, which is 2.5. I'm going to divide. Look at how clever we can be with numbers. And then I have 12.5 divided by 5. Oh, it's 2.5. Yes. Don't get scared on the next one here. Don't get mad. It's going to be okay. This doesn't fit. I don't write small enough to make this fit. All right. And then I try 31 divided by 12.5. What do we get? I mean, like, kind of. It's like 2.48. And then I go again, and I get 78 divided by 31. which is like 2.52. And you're like, but they're still not the same. Here's the really rude part about this, is that because of rounding, like let's say this number was actually 29.89. No, I'm sorry, 30.89. It was like just a little bit less. And they rounded to 31, which would cause these numbers to be off a little bit, right? Because this is only off by 2/100ths, and this is off by 2/100ths. It's such a small number that like it's okay. So here's one thing about this is that common ratios can be exact or approximate. Approximate would be like close. And so this is close enough. This is a common ratio. I think the ones in your assignment are exact, if I remember correctly. So common ratios can be exact or approximate. They might just be really, really close. I mean, if I rounded these two numbers to the nearest tenth, they would both round to 2.5. Okay. All right, so when given the table, you're going to analyze the Y column, right, to find out if they have the common first difference. If yes, it's linear. Common second difference. If yes, it's quadratic. Common ratio. If yes, it's exponential. All right, and then real life, let's talk about like where these actually show up. Linear works really well in theory. A lot of these work really well in theory, right? It's kind of the perfect scenario. And so if I have a common increase or a common slope, this could be like add $3 to a piggy bank each week. All right, so if every single week you put $3 in the piggy bank. Whoa, I'm throwing things. Then you would have a linear function. Or let's say every single time you go to, I don't know, Chipotle, you order the same exact thing every single Wednesday, it costs you $12, right? That'd be minus $12, minus $12, minus $12 every week, right? That would be linear. It'd be a common change, a common difference. Real life example of exponential growth would be, so bacteria growth is a common way we look at exponential growth. Population growth, or like money in some kind of an interest earning account. Like if you have money in a savings account that earns interest, or money in, I don't know, a CD that earns a certain percentage of interest. Exponential functions don't always have to be growth. And so this graph in this example, it starts small and then it shoots up, but it could flip, right? It could come this way and it could also just like head down really steeply. It doesn't have to go up. It could also be exponential decay. And when we look at exponential decay, we talk about things like half-life or carbon dating, things like that. From your good old science classes. And then common real world examples of parabolas. Like I said, it's usually the parabola with a negative a value, and be like the path of a kicked soccer ball, assuming it left the ground, or a rocket. Hopefully you already wrote on your paper somewhere that exponential is greater than quadratic, which is greater than linear growth.